All right. Coming in okay? Thanks, everyone. I appreciate the good turnout. So today I'm going to be talking about kind of the intersection of applied security and a lot of the developments that have been going on with emerging encryption in databases. This is a talk really geared towards architects and defenders. This is not math heavy. It's not any new crypto that's being introduced. It's really trying to kind of bridge several different emerging areas where even among I think a lot of expert engineers, there's a lot of misunderstanding, both in terms of like commercial products, open source, really popular databases, as well as sort of what's practical and what companies and organizations are really adopting. So hopefully you'll come away with some understanding of those two insights kind of bridged. Oh, I'm Ken White. This is probably the best way to ping me is on Twitter. By way of background, I think some folks know I've been involved in large-scale global architecture, safety critical systems for 20 years or so. If you've taken any new drug compound that was developed in the last 15 years, there's a pretty good chance that it went through one of the systems that I built. So a lot of focus around protecting really sensitive workloads, healthcare data, clinical data, some law enforcement work, a little bit with Homeland Security. And sort of on the community side, some of you may know the work that we did through the Open Crypto Audit Project with the True Crypto Audit, with the Linux Foundation, and with the OpenSSL audit. So, but I come at this from kind of a different perspective. My background is really more in signals engineering, and most of the sort of applied encryption and network security was sort of developed along the way. It's I'm not a academic cryptographer. Anyway, just recapping, these are some of the goals. In conversations I have with really talented people with great insights and depth in their fields, it's clear to me that there's really a lot of misunderstanding, I think, when people talk about encrypted databases. And so hopefully we can sort of break that down a little bit today. I do want to look at some emerging methods. We'll talk briefly about some academic things that are developing, but really I want to focus more on sort of, practical implications and sort of success patterns that we're seeing emerge. And again, this is really oriented towards architects and defenders. So let's take a quick tour down the history of database encryption. Almost every time there's a major breach with, we saw this with Anthem and with Equifax, there's always some pundit that gets on and the headline reads something like, if only the database were encrypted, this wouldn't be a problem. So, and you sort of see that, part of it through marketing and sort of product, marketing and management. I sort of understand that, but when we talk about encryption, it's one of the first questions to ask is, what are you encrypting? At what layer? So I think it's pretty common that most access from clients, either native clients from developers or through web applications, are these days hopefully connecting with secure transport. In the early days, Oracle and Microsoft sort of developed some native kind of quirky sort of modifications of encryption over TCP, but pretty much most of the primitives now under the hood are reasonably modern and properly constructed TLS. So storage, volume encryption, this seems to me to be sort of a basic thing, but there's a lot of misunderstanding. Almost every cloud database, the major three, that Amazon, Google, and Microsoft, you'll see this all the time, that your data are encrypted at rest. But that's really useful for laptops and for desktops, I guess, with sensitive data. But one of the points I want to make is that volume encryption kind of addresses the eBay and Craigslist attack, right? So when servers are retired and they're repurposed, they sit on a shelf for a few years, and then eventually someone buys them and says, oh, look at all these social security numbers and credit card numbers and insurance records and things. While it's true that it's an important control, it prevents sort of petty theft and leaks that way. It's only a tiny step. So I'm assuming that for any deployed production database that volume encryption is just a given, and you should too as defenders and architects. That's definitely not always the case with some of the mid-sized cloud providers. Even, I think it was 2.5 years ago, on a not big three, but a smaller tier, but well-known infrastructure as a service provider, I was playing around with actually de-encrypt and was trying to do some sort of simple exercises, and I just did a cat on the low, on the raw volume, and I started getting all kinds of like classified ads and like raw SQL statements and data and dating profiles and stuff. Well, it turned out this company used SSDs, but they didn't wipe the disks between provisioning, and they didn't even encrypt it. And actually, that's the other thing too, is that you'll talk to some kind of more seasoned auditors sometimes, and people spend a lot of time sometimes about disk destruction. It's kind of not an issue if the volumes are encrypted. If you destroy the key, then it doesn't matter if you've done a write over one time or however many times to keep the auditors happy. If you've got full volume encryption and the key's gone, then the data are destroyed. And increasingly, the guidance from NIST and from the payment card industry, I think, is starting to reflect that. So as sort of, really mature database management systems kind of evolved, one of the first things that was developed is what's sort of, it's kind of confusing because it's you can capitalize or not capitalize TDE, but transparent data encryption. So the idea is that, okay, you've encrypted the disk volume that, where data sit, but within that, is there a way for a database administrator or people who do, have some operational oversight to not be able to see application data? And so, there have been attempts at sort of multi-key and some other schemes. Oracle has like an encrypted wallet. Most of the commercial databases have ties into key management protocol for hardware security modules, for HSMs for keys. But really, you're not, it's kind of a weak model, because what table level data encryption does is says, okay, we have to log into the database and you have to have some access privileges within a database, and then you can see the plain text. Okay, well that is one layer, and maybe that's helpful for certain use cases, but it's not, it's not the strongest. The strongest type of encryption you can do is client side, where from the application or the driver side, data are encrypted. So what's seen centrally in the DB is this ciphertext, right? And these are just some examples of sort of popular databases that have those. With Microsoft and their sort of evolving models for SQL Server, they've, over the last few years, enabled a new feature. I think Senny Kamar, who's now at Brown, was part of the team at Microsoft Research that really helped kind of build some of this. But transparent data encryption, server side as well as client side. So what that means is there's two sort of common modes that you'll see out there. One's deterministic and one's randomized. Deterministic is if my social security number is 673, then it's always going to encrypt to foo. 673 is foo, 673 is foo. So every time that's encrypted, it's the same ciphertext back. And that's useful because then you can index it and you can do point queries and you can do other SQL semantics to get those data back. The stronger form is what you traditionally think of in encryption, which is regardless of what the plain text looks like, the ciphertext should look differently. And so that's randomized encryption. And the primitives are pretty standard. I mean, this is AES, CBC construction, sometimes GCM. The problem is if you index that, then you don't really have anything. You can't, your database isn't terribly usable. So if, for example, you encrypt on social security number, but you use traditional randomized, like AES encryption, and you say, select blah, blah, blah from where a social security number is X, it doesn't work. It would work if you did a full table scan and did tons of traffic back and forth, but it doesn't work in the traditional sense because you can't index it. Because that social security number, if it's represented more than once, is going to be encrypted in a different way, and so the index doesn't work. So strongest controls available are randomized encryption, which means, from a confidentiality perspective. But the trade-off is you have to do a point query, range sorts, things like that on other columns. So sometimes there are use cases that allow that. If you've got a really rich set of tables and maybe only a couple of fields, a couple of columns that need that, card data or something else, that may be useful. But mostly people are turning on deterministic encryption. Also, Microsoft, I don't know if people have followed this closely, but the Intel SGX Enclave, the sort of built-in crypto module that on some of the newer Intel chips, Microsoft is doing a beta version where you're essentially doing server-side encryption and you're delegating your key. It's strongly sandboxed, it's strongly contained within that SGX with some caveats. There are some attacks, including phoning home from Intel, like hardwired in the chip. That's a different talk. But as far as I'm aware, that's not sort of for general release yet. It's something that is sort of still in preview, and in any event, it is a delegated key model. Something that's pretty promising and still exists to some extent in libraries and things is CryptDB. This was Papa and several folks at MIT kind of developed this. It's kind of a mixed model where some types of encryption are randomized and others are deterministic, and it's highly performant. I think elements of that were used in some early versions of SQL Server. I'm not sure if that lineage still exists. Google did some work with encrypted BigQuery, but again, these are, it was a proof of concept study, and as far as I'm aware, and I've been looking deeply and talking to the Google product people, as far as I'm aware, there's not a client-side encryption model now. So there was an encrypted BigQuery where data are encrypted plain text before they go centrally, but and it still exists on GitHub, but as far as I know, it's not a commercial offering, and I think it's because of performance. But again, in the BigQuery models that services that are available now, it's custom managed keys that are delegated to the cloud provider. Oracle also, both through Amazon and as well as Oracle's cloud, allows you to do transparent data encryption at the column or the table level with key delegation. Postgres, I'm hoping that there's going to be some interesting developments in the next year or two, but because right now it's kind of roll your own. It's, there are SDKs and there are things that people use, but the docs basically say, well, just do PGP, encryption and then, build it into your app. And that may work if you're starting greenfield. It may work for certain use cases. The problem is you've got to do a pretty heavy amount of application code modifying, right? If you're constantly putting helper functions in or calling special methods to encrypt decrypt, in any event, it's still going to be server side with the techniques that are available today. MongoDB, a lot of people don't know this, but there's an encrypted storage engine through the Wired Tiger storage engine. There's two flavors of that. One's enterprise, the others, they're cloud managed. Atlas disclosure, I think I had this in the background. I'm on the product group at MongoDB, so I have some insights into this. The current model is similar. It's a customer delegated key. It uses Amazon's KMS or Azure's Key Vault, which upstream use hardware security modules, but it is a delegated model. The Enterprise edition can do native integration with HSMs through the key management interface. I don't know. With Amazon, at the speed of things that things are changing, who knows? But right now, across their managed databases, as far as I'm aware, it's pretty much all server side, so delegated keys, or purely Amazon managed keys. To their credit, Amazon has an incredible security team. They have, they've written their own native and formally verified, crypto library that is, gone through all kinds of reviews and testing. But for client-side encryption, your option right now is pretty much a software development kit and kind of, roll your own through your applications. So I mentioned before, one of the things that was kind of promising was this work out of MIT, the Palpa group with CryptDB. Let's talk about that for a second. So, well, actually, there's several lines to this. So as I mentioned before, one of the models with centrally managed and key delegated is I'm going to limit what a DBA can do. In almost every database system, somewhere there's a root user, somewhere there's a master god, global cluster admin, something. So that level of access can almost always create another user and then promote that user, grant privileges. So it's almost like a junior DBA versus a senior DBA. To be fair, in some organizations, there's strict operational control. So like these really large implementations of Oracle and SQL Server, you see this in healthcare and banking and the defense sort of world. You literally have a group of DBAs. Their job is to patch. You have another group that does application database administration. And you have another group that actually does like sysadmin kind of DBAs. And I've seen in some implementations, it's not unheard of to have OS level credentials and Kerberos credentials and application level credentials and then local DB credentials. And all those have to be in sync with some of the middleware products, not to mention the integration with key management systems, whether it's hardware modules or otherwise. So format preserving encryption we'll look at in a minute, deterministic as well. I'm not sure folks are familiar with tokenization. This is commonly used in the payment industry, so for PCI data. The idea is that it's not necessarily a cloud issue or a central administrator model issue, but it's just that you don't want to store raw card data, plain text, and so it's tokenized. There's consistent tokens. In that sense, it's pretty similar to deterministic encryption. There's also cloud access brokers. These are services that sort of have some insight to how, for example, Salesforce works or particular application, and they're tightly integrated with that service provider, and so they just sort of do on-the-fly proxying for encryption client side. So that, for example, Salesforce or Google or whoever else, essentially all they're getting is ciphertext. So what are the problems with trying to prevent one DBA from seeing things that another DBA doesn't want them to see? There's a great blog if you're into Oracle kind of architecture or security that's worth a read. This guy, Robert Lockhart, so he demonstrated, this has been a couple of years, but it's absolutely still true in most deployments now. So I'll point you to the create section. So this is just an example. This is one of these dummy data generators that creates fake names and fake, credit cards and so forth. So this is real data. But anyway, it's a simple construction. So, here's first name, last name, and so on. And then, here's what it looks like from Oracle speak. So credit card number, social security number, those are encrypted columns. Unfortunately, Oracle has this thing called histograms, which most databases have something like this. It's a high-performance statistical analysis that sort of helps with load distribution, helps with index creation, and so forth. So the data are encrypted, but the histograms are not. It needs to be able to work on the histograms to know, for example, that the person with the first social security number is in 4 times or 20 times or whatever. So by querying on the histogram rather than the underlying data, you get plain text back. And then taking it one step further, you get the entire record back. This is having no idea what the key is, no idea what the application was doing, just give it to me.
format preserving encryption. Sometimes in legacy systems, you've got really, really deep investment in 10, 15, $20 million applications that do some kind of processing or some kind of like service bus integration with a really, really old legacy, but sort of revenue crucial kind of interconnect. And so sometimes architects have been challenged to say, okay, I need you to encrypt a credit card number, but you can't have the field any wider than the original credit card number. Okay, that's kind of tricky, right? Because encryption changes the size of the plain text. So NIST put out a call and had sort of competition and invited feedback. They created several models for this format preserving encryption, FF1, FF2, FF3. FF2 didn't make it quite to the final round. They were just constructions. They were do this with AES and this with a hash and this kind of index and so forth, and stand on your head and the sun's the right position, then the width should be the same. So this was March of 2016. April of 2017, oh no, let's FF3 is broken. Let's not do that. So this is this is tricky stuff. There are some really interesting attacks against these, and so this is very much an emerging field, and it changes quickly. So this line from one of the press releases, this is another security vendor, but I thought this was interesting. So FF2 didn't survive publication. Now FF3 has been broken by researchers, but in the span of a year. So it's a tricky engineering challenge. When I look at a lot of customer deployments, this is kind of what I see, right? So I'm using an encrypted database, but the keys are on the database, or worse, they're hard-coded, on that system. I mean, it's a joke, but it really, if you look at what the data flows are to return plain text data, this isn't too far from reality for a lot of implementations, I'd argue most, actually. So let's go back for a second to look at that work from Papa. This is not an exaggeration. So in the last couple of years, there have been attacks against deterministic encryption, which again is the major mode of encryption for commercial, the larger database products out there. They effectively broke it with a technique that monks developed in the 800s. So if you, for example, use deterministic encryption on a really large pool of credit card numbers or social security numbers, you're probably okay. The histogram is flat and it's wide, and there's not a lot of curve. If, on the other hand, you take, for example, published Medicare data, hospitalization data, millions and millions of records, where there in fact are only a few, not a few, but there's a known universe of social security, of zip codes, of states, of genders, of pancreatic stage 2 diagnosis codes, ICD-9 codes, and so forth. If you do that, 60 to 80% of records can be decrypted, purely based on some a priori information about population distribution, right? So if you have a gender field and it's MF, 3 values for, whatever, and you know that in a certain country the gender spread is a certain way, then you can make inference attacks on what those encrypted values are, even though you don't have any idea what, what's actually there. Then if the database is using the same key across columns, across tables, you can similarly do deconstruction. For those, it turns out that fields that are not flat histograms are the majority of encrypted databases. They certainly are in healthcare and in some of the financial systems that people have looked at. at the end of this, if you're interested, there's I've linked to several talks from real world crypto and some academic papers, but it's worth looking at. I mean, these were devastating. Up to 80% of these data could be reconstructed with high assurance. Grubbs, Rissenpart, Shamatkov last year published a great paper called Why Your Database is Not Secure. Highly recommend. But one of their points was that, okay, a lot of the published academic papers talk about snapshot attacks. Do people know about VMware Live Motion or Google's cross-cloud live migration? So the idea is that normally, when you think of a VM backup, you take a snapshot of a running volume, copy that somewhere else, and then reboot the volume. What VMware Live Motion does is also does memory snapshots. So state of the disk, state of buffers, state of memory, state of registers. So you can literally take that instance and move it over the wire and bring it up somewhere else. That's really interesting. But it's a problem if you think about what's happened from an encrypted database perspective. You've on disk stored encrypted structures, but in memory, if it's server side, they've been decrypted, or at the very least, the keys are in memory. And so those snapshot attacks, a lot of encryption, database encryption models were built to protect against those snapshot attacks. And part of what Grubbs and company showed is that, yeah, that's one viable attack, but if somebody's that motivated that they're either in your data center or they're at the cloud operator and they've got that kind of visibility into literally processes and memory, maybe that's not as realistic as things like logs and diagnostics and in-memory structures. And so they sort of tear that apart. Anyway, it's a great read. Which brings us back to threat model-driven design. Are we protecting against a disk being repurposed and showing up on Craigslist? Are we protecting against an insider DBA? That's harder. Are we protecting against backups that were sort of misapplied and they're somewhere else? Are we thinking or have we not thought about web application security, right? Because you can have like post-quantum crypto, the best in the world, but if your web app has full access into that, and it has transparency into the key management system, or it brokers all keys, or worse, you've got one key with full privileges, and that's compromised because of a SQL injection or something like that, then maybe you're not thinking about this in the right way. Hardware security modules are used in cloud key management systems in a very particular way. So the idea is that you have a small payload, maybe a public key or a data encryption key, and maybe a key wrapping key. It's called envelope encryption. So that's handed off. The cloud broker sort of with the HSM decrypts in the HSM and then returns back. So that's useful for lower scale key generation. It's not really practical for high volume, data set returns in SQL. Actually, for a lot of SQL semantics, it's a non-starter. But it may also not matter, right? I mean, a lot of the models assume that there's individual users, so every single user has a special key. That's sort of like it's almost like a client-server kind of model, and maybe that's the case, but an awful lot of deployments in the world are web applications, right? And so the security of that entire structure, that entire flow, is only as strong as the web app protects against. And again, RAM is the Achilles heel. If I've got encrypted central server side, and I've got table space and down to the column level that's encrypted, if I'm a sufficiently interested or bored sysadmin or DBA, I can scrape memory, I can look at other processes to leak those keys. One of Rissenpart's points with the snapshot attack is, if somebody's gone to that much trouble, there's probably 20 other ways to get in. And if you're not thinking about those, then that's a problem. There's a final school of thought that says it doesn't matter. I don't care if it's a court order. I don't care if it's a discovery motion. I don't care if it's a nation state. I don't care if it's I don't care. I want the highest level of confidentiality from an app that's possible. If that's the case, that's client-side encryption with some type of homomorphic encryption. Unfortunately, we don't really have full homomorphic encryption in any kind of wide use today for the more popular databases. It's certainly evolving quickly. So we were speaking, even 2 years ago in terms of minutes. Now we're talking milliseconds. So those sorts of efficiencies. But the problem with a lot of client-side encryption is that you have to build a lot of, first of all, you're not going to bolt on to some existing legacy system, right? You're not going to bolt on to a MySQL or MongoDB or, Memcache or something like that. It's just not going to work. You have to have deep insight into the semantics of data structures. And also with what are pretty promising, but still kind of nascent technologies, you've got to build indexes, you've got to build partial trees, lots of sort of guts and things on the client side, and that's tricky. In the case of SQL Server that I mentioned, the always encrypted engine, that only works for, I think, like 3 or 4 drivers, and it's a fairly heavy load. So the client is taking a fair amount of the computation. But that's what I mean by zero knowledge. The idea is that there's some amount of heavy computation that can be done centrally, maybe a cloud provider, maybe somebody else in a data center, right? Because a lot of financial institutions and things of that sort, I work with some mobile companies that have, for example, somewhere in the bowels of their organizations, the systems that manage keys for millions and millions of cell phones, right? So that's not a matter of I don't trust someone or we don't have the right controls in place. This is a catastrophic end of the business if these data are breached. So we have to have some tools where there's a zero knowledge model, where the operator, where the database server side has zero visibility. I think I've got it linked too. There's a couple papers from Google and Amazon in terms of key rotation and what some of their lessons from scaling up their key management structure. In all likelihood, the vast majority of people in this room, you don't have Google and Amazon's, volume, but a lot of the lessons were really interesting in terms of where they originally hardened their access points. So you do the standard things. You do rate limiting. You do sane checks on, single source IPs. You have a rational permission model. But all that, you still got, it sort of turtles down. There's bearer tokens somewhere in that stream. If you've got a really well-architected and constructed hardware security module, but at some point it has an API, if that API is breached, then you've effectively breached the HSM. So again, back to first principles. Sane defenses, rate limiting, segmentation, real-time anomaly and detection. So when you see these things, as we did the other day, from, 2, 3, 4 years, insiders in the system before detection, there's other things going on that are probably going to trump the kind of, those security models. Savage key segregation. And by that I mean, in several server-side models and client-side models, actually, there are field-level keys that are stored with envelope encryption, with wrapper keys. Those have to be really, really carefully guarded. So if you're building systems or you're working on a control plane or you're involved with sort of large-scale integration, crucially important to understand what that operator sort of visibility is, right? If you've got great hardware, you've got really modern, minimized surface, but then there's some kind of orchestration layer that does all the, in chef terms, bags, vaults, other things of this sort. You really have to think about what those exposure paths are. And this really is the problem, right? Cryptographers sort of course you use same key management and identity policy, but I can't tell you how many large Fortune 50s I've walked in, and that's the model, right? So they're one SQLite injection, SQL injection from complete compromise, even though they have the $100,000 hardware security module, even though they have all the next gen malware stuff or whatever. It's crucial to model what those attack threats are and how realistic they are, what the likelihood is, and what the severity is if they're breached. If you come away with no other thing from this talk, I hope this is this. It's obvious maybe to some security people, but hard-coded credentials, single point, master control, full access, it happens all the time. It happens with third-party products, it happens with integrations, it happens everywhere. So the stronger the segmentation you can make it for who has access to those keys or the data encryption keys, the encryption keys, the better. I've been involved in a pen test fairly recently where there actually was a pretty good key management layer in place. There was pretty good orchestration, but there was a single point where it wasn't a DBA user, but effectively the web app might as well have been a DBA from that, from that vantage, because when the application got popped, then the entire database you could do a select star and come back. So that's some of the things that are developing, but maybe a lot of like bad news. So these are things that are emerging that do look promising and that I want to spend a minute talking about. Secure Enclave, as I said, it's not a cure-all, it's not a silver bullet, but it is another interesting level of key segregation within servers if the model is a key delegation model. Geo-attestation, this is something that's actually built into a lot of system boards now, and with things like the i2 instances that Amazon has sort of been rolling out, you can do literally bare metal. You can provision bare metal, which means you can access the VTX modules and the geolocation. So that means, for example, you can actually say, not just by IP, but by public key attestation, this is the only thing allowed to talk to me. Temporary credentials, instance-based identity. This isn't, it's not, that has, strictly speaking, it's nothing to do with database encryption, but temporary credentials and instance-based identity is a really powerful technique. It's available on all the major cloud platforms. As far as I'm aware, there are solutions like that on VMware's control plane. It takes a lot of the hard and heavy lifting out of your hands, and it just works. One of the caveats, though, is if you build up, for example, a Kubernetes cluster, then everything running on that VM bears those temporary credential tokens and so forth. Sane full disk encryption. I've literally seen support how-to articles from database mid-sized companies that say, put the key to the full disk encryption volume in whatever, at C, and then just load it from there when the volume boots. It's like, all right, that's wrong. With homomorphic encryption, as I said, there's really promising work out of Brown University, Microsoft Research. I'm already aware of several large tech companies that you all would be familiar with that are using attribute-based multi-party encryption. So the idea is that, thanks. So the idea is that I'm a role of insurance adjuster in the Eastern region, or insurance adjuster in the Eastern, in Kentucky or something, and those two attributes together are enough for public key decryption. I've got a link at the end on some of the work that Matt Green and company's been doing. That is in the sort of early adopter phase now, but I think we're going to start to see it roll out into bigger products. So finally, the takeaways. Most of the security models around encrypted databases are either weak or they're underspecified. Encrypted volume disks, are great, but it's like very basic, table stakes. And they're not protecting you from Amazon, Microsoft, or Google. They may protect you from their customers, but I don't even think that's true anymore. I think that all the major 3 providers are now doing volume encryption by default now. You may have to think about court order discovery, far more likely probably from people in this room than you would sort of a nation state attack, right? Because court orders come to a provider and they need to do preservation. Crucially, you have to think about key surface exposures. Again, the best technical measures and controls you can put in place are only as good as those exposures for the keys. Have to think about AppSec, have to think about SQL injection, bearer tokens, API intercepts, backups, logs, sysadmins, and DBAs. All right, that's it. Thank you. I am happy to take any sort of dive into more technical questions too, if folks have it. Anyone? Not a single question? Everybody's happy with their database encryption? All right. Well, I'll be around the rest of the day and tomorrow, so feel free to come swing by and chat with me. Happy to talk. Thanks.